Hello class, today we're going to do a spring potential energy conservation of an energy problem. Okay, so if you hadn't already, go back in the video and copy down the original problem. So we have a spring-loaded gun with a dart. I represented the dart as a circle and it's being compressed a total of 0.6 meters. Okay? The mass of the dart is 1 kilogram and the spring constant is 250 newtons per meter. And once again, it is being compressed a total of 0.06 meters. So in order to start off with these kinds of problems, you need to start off with the conservation of energy theorem. Basically, it says the energy that you start off with is the energy you end up with. So a very important thing to remember is the conservation of energy theorem, which is the potential energy, U, plus the kinetic energy, is equal to the potential energy plus the kinetic energy, final. Now, you can see potential energy in two different ways, PE or U. I personally like U. Okay? Now, this is for any object that's up in the air or that's moving. However, we're dealing with springs, so we also have to include the potential energy of a spring. So I'm going to write that as U sub S. Okay. Now, anything on the left-hand side is the initial, and anything on the right-hand side is the final. So I'm going to write the subscript O for initial. So it'll be U sub SO, U sub O, KEO, and F for final. U sub F, KEF, U sub SF. Okay. The equation for a spring potential energy, or for us, U sub S, is going to be 1/2 kx squared, where k is the spring constant. Okay? And the equation for potential energy is mgh. The equation for kinetic energy is 1/2 mv squared. Now, because it's initial, I'm going to make that VO. All right. U sub F is the potential energy final, which is mgh, plus kinetic energy, 1/2 mvf squared plus 1/2 kx squared. Okay. Now all of this on the right hand side will be the final, and everything on the left will be initial. So let's plug in the variables that we know. Okay. We know that in the beginning, for the spring constant will remain 250. Okay. And it is compressed a total of 0.06 meters. So that will be my x, 0.06 meters squared. Now in the problem it said that assume that this spring-loaded gun's height was 0. Okay, that the potential energy line was 0. So the potential energy here, mgh, the h is 0, making all of this 0. Okay, plus 0, plus 1/2. The mass for this spring or this dart is 1 kilogram, and the initial velocity for this dart would be 0 because it's not being fired yet. It's just locked and loaded. Right? When it is fired all the way through, because it's along the same height, and we said the height was 0, its potential energy will still be 0, plus 1/2 m, which was the mass of the dart, was still 1, velocity final, which is, I believe, what we're looking for, plus 1/2 k, which in this case was 250, times x squared. Now, x is the displacement of the spring, and when it is released, the displacement will be 0 because it is no longer compressed. Okay, it is fully uncompressed, so 0 squared. So numerically, this is what we get for the conservation of energy formula. What this means, I guess in words, is that in the beginning, we have some amount of spring energy. Okay, the dart is pushing against the spring, and the spring has all this energy just stored inside of it. Okay, and it is at a height of 0, so there's no gravitational potential energy, and it's not moving, so it doesn't have any kinetic energy. So once we pull the trigger and the spring unleashes or unloads, it'll shoot forward. Now when it is shooting forward, all that spring energy turns into kinetic energy because it's moving, okay? And that's represented here mathematically. When it is fully uncompressed, there's no more energy in the spring, okay? So all of this would equal 0, because when you multiply 0 times 250, 0 times 1/2, we get 0, okay? So there is no more spring energy, and instead all of that energy turns into kinetic energy, all right? So we can actually find out how fast this object is moving if we do some math. So if we do 0.5 times 250 times 0.06, we get 0.45 joules plus 0 plus 0 is equal to 0 plus 1/2 VF squared plus 0. So the total amount of energy that's stored within this spring is 0.45 joules. And if we multiply both sides by 2, and then square root both sides, okay, to find V sub f, we find that V sub f, or the final velocity of this object, is 0.95 meters per second. Okay? Try it out on your calculators at home and see if you can get the same final velocity.